Alright, welcome everybody. Today I'm going to cover section 1.3, differential equations as mathematical models, and, sorry, I got some stuff popping up on my computer. And essentially, when we're talking about mathematical models, these are mathematical descriptions of natural phenomenon. Okay, that's what a mathematical model is. Okay, and oftentimes those mathematical models relate certain quantities or characteristics of that system of phenomenon, such as we're going to be looking at the general form of population models as differential equations, radioactive decay, Newton's law of heating and cooling. We're going to look at mixtures containing a salt solution. We're going to be creating mixtures with solution flowing in and out of the solution, causing a mixture to form. And that's going to be the, I guess, prototypical example that we're going to use in this section. This section doesn't really do a whole lot other than have you set up differential equations for all these different models. You might be asked at some point to solve for an arbitrary constant given an initial condition. But again, we're going to learn how to set up and solve these differential equations in more detail in later sections and chapters when we're actually learning, more forms of differential equations and specific methods of solving them that apply only to those forms. Okay, so let's start maybe looking at what these models are. Okay. So again, you have population models, you have, this is going to be to a situation where the rate and change of population, say, with respect to time. Okay, so you're thinking of population as a function of time, and the rate of change of that population with respect to time is proportional to the population at time t. Okay, so for instance, with a lot of population models, you might have this happening. Now, if you look at the left, it says the rate of change in population with respect to time would be, say, dp dt or p prime. To say that is proportional, okay, now proportional to the population at time t. So proportional to the population, when you are proportional to something, or more specifically directly proportional to something, it just means that you are a multiple of that something. So in this particular situation, if you have a population model where the rate of change in population is proportional to the population, okay, which is generally true for many populations, and this is where, of course, k is a constant. Okay, so that would be just your that would be your differential equation that you would solve. You would at first solve this differential equation by finding the family of solutions, and then an initial condition on the population would allow you to solve for that constant k there. I want to make one more comment about population models. I think just a minute ago I said many populations can be modeled with a mathematical model such as this. I want to say that is actually not true. I just double checked. Populations that are modeled in this way are still used, but they're still rare. And it says that, if you look in the textbook, it says that even if people use a model like this for a population, it only does really well at predicting populations over short periods of time. Thought that should be mentioned. Now, radioactive decay, which is more accurate and also involves proportionality, this time it says the rate of change of the amount of a substance with respect to time is proportional to the amount of the substance at time t. Okay. Now, anytime you have quantities related to each other with respect to another variable, such at time, and basically the amount of a substance at time t, and it says how that's related to the rate of change in the substance with respect to time t. That's kind of telling you that there's a relationship between the dependent variable, the independent variable, and its derivatives. Okay, so right away you're thinking differential equation here. Now, you'd have to introduce some variables. So it says, on the left, it says rate of change in the amount, and I'm not going to be very clever, but for that I'm going to write dA for change in amount over dt. That's just telling me that that's the derivative with respect to time. Okay, so you know the derivative of the amount with respect to time, and again, that's supposed to be proportional to the amount at time t. Now you can write a, or you can write a of t here, and again, this is where k is a constant. Okay, and this is probably a better model than the population model. Radioactive decay is oftentimes, proportional to the amount of a substance at time t. It is going to, I believe, turn out that models of this form, the function for the amount, actually end up being like logarithmic or exponential, probably exponential. We know that radioactive growth and decay, if you've modeled those from pre-calculus, those are modeled by exponential functions, okay, or variations of exponential functions. And again, if you want, you might be given the solution to this, or you'd have to find the solution. You'd have to use an initial condition to find the constant of proportionality, or possibly some other information. Okay. Okay, and one more thing about radioactive decay. So, again, usually the rate of change in the amount of a substance with respect to time is proportional to the amount of the substance at time t. The last thing I wanted to point out is that whether it's a population or we're talking radioactive decay, when the rate of change is proportional to the original amount in this way, when k is greater than 0, you see growth, and when k is less than 0, you see decay. Before I talk about Newton's law of cooling, I do just want to point out that as you're reading through the beginning of the section in the textbook, differential equations as mathematical models, just one thing to keep in mind that's kind of actually interesting is looking at this feedback loop for improving mathematical models. Especially this part where you start down here, you would display model predictions. So you have some predictions about your population or your amount or your temperature. We're going to see Newton's law of cooling in a second. We're going to talk about modeling circuits. And after you display those model predictions, you could check your model predictions with known facts. So you're going to compare observations to any of your predictions, and then if necessary you would alter your assumptions or increase the resolution of your model. Okay, and then you're going to express those assumptions in terms of a differential equation, solve the dE to obtain a solution, and then just start this feedback, continue this process. Okay, display model predictions, and then as new facts come in, compare your model to known facts. Okay, alter the assumptions, and then again express assumptions in terms of differential equations. So there's this interesting feedback loop. For people that are actually interested in mathematical modeling, I know there's a lot of mathematical modeling that takes place with population genetics and biology and things like that. Okay, and then next we could look at modeling Newton's law of heating and cooling with a differential equation. And Newton's law of heating and cooling states that the rate of change in temperature of an object with respect to time. Okay, again, that's telling me about the derivative of temperature with respect to time. What if, well, we actually know this law. We know that that's proportional to the difference between the temperature at time t and the surrounding area. So I'm going to introduce some variables here. Temperature is going to be T. T is the temp at time T. Lowercase t is time. Okay. T sub m is going to be the temperature of the surrounding area. Okay, so the temperature of time t, that's the temperature of some object. Okay. Tm is the temperature of the surrounding area. Now, these capital T will be a function of lowercase t, but T sub m could be, that could be a constant function. That could also be a function of time t as well. And then, of course, I believe those are the only three variables I need. So what this is saying is the rate of change of the temperature of the object with respect to time, that is supposed to be proportional, i.e. a constant multiple of the temperature of the object and the difference of the temperature of the object and the difference of the temperature of the surrounding area. And again, capital T is for sure a function of time t, but the temperature of the medium itself, again, that I guess that we'll just think of that as some arbitrary function of time as well. Now, if the temperature of that medium, or the temperature of the surrounding area, if Tm is constant, for instance, it turns out that K will always be less than 0. And you can think about it this way. So like, okay, if you have, say, cooling, okay, why does K have to be less than 0? Well, if you look down at the differential equation, if you are cooling, this rate of change should be positive, right? dt over d lowercase t is positive. Sorry, being a fool. It's got to be less than 0. Okay, the temperature, the rate of change would be decreasing. Okay, well, this quantity right here, if you are cooling, the temperature of the object is going to be greater than the temperature of the medium. So in that case, for cooling, this is actually positive. Actually, let me write this down here. I'm out of room. This quantity is actually greater than 0. The first one. Okay, well, if you're supposed to get dt, or the rate of change, to be less than 0, and t minus tm is greater than 0, that means k has to be less than 0. Okay, well, if you're warming, let me learn how to write. If you're warming, okay, dt over dt has to be greater than 0. Okay, well, let me erase this and rewrite it for a second. Okay, why does that imply that k has to be negative? Well, dt over dt is k times t minus tm. This quantity right here, if you are warming, this has to actually be less than 0. Okay, you're warming, that means the temperature of the medium is greater than the temperature of the object. And if that's less than 0 and you're multiplying by k to get a positive quantity, again, k must be less than 0 as well. Okay. So there's Newton's law of cooling again. We can solve differential equations of that type. We'll do that in later sections. It's actually not too difficult, depending on the temperature of the medium. Okay. And the last one that we're going to look at is mixtures. And one thing I want to point out about this is this is probably, to me, the most interesting example, and we're going to do these again in Chapter 3. But this is also one of the only problems that they actually do a specific example of in the textbook. And there are several other different quantities or phenomenon that you can model with differential equations. I didn't cover them all here. You can read about the rest in the textbook. And I'm going to focus specifically, I'm going to do an example setting up a differential equation for a mixture situation. Now what it says is, it says up here, if you read about mixtures, is the rate of change of the amount of salt in the mixture with respect to time. Read this carefully. It's the difference between the rate of inflow of the salt minus the rate of outflow. Okay, so the only way you can really start this, and you have to really phrase this generally because there's no real general form to this, but you can say that the the amount of salt could also, it's actually the literal amount of salt, not the concentration, so like how many grams of salt are in the mixture. And the mixture is usually going to be some brine solution, so water that actually contains some amount of salt. But the rate of change of the amount of salt in a mixture with respect to time is not proportional, but it is the difference between the rate of inflow of the salt minus the rate of outflow of the salt. So what the textbooks, actually the way they write this is they call this Rn for the rate of the inflow, and it's minus the rate of the outflow. Which actually I think they're just calling R out. Okay, so that's the rate of inflow, the rate of change of the amount, and again that makes sense because if you take the rate of salt coming in and you subtract the rate of salt going out, you should be left with the rate of change of the amount of salt at any moment of time. Okay. And I'll maybe further expand on this a little bit. Rn, okay, so there's a way to find the rate of inflow. So be careful. One thing, before I move on, I should say this. The rate of inflow of salt, so this is how much salt is coming in per unit time. And the rate of change of the outflow of salt, okay, that's the rate of change of how much salt is leaving. Now when you actually, let me clear all strokes here. Let me make some room for myself. Okay. So again, what I said is Rn, this is the rate of change of salt coming in, and then R out is the rate of change of the salt leaving. So when you write dA dt, again it's the rate of the inflow minus the rate of the outflow. I'm just going to write Rn for example. It's the same for R out. This would be the concentration of salt in the inflow, but then you'd have to multiply that by capital Rn, and this is actually the this is the rate of inflow of the mixture. right? So like maybe you know how many gallons per minute of the mix of some solution is coming in. So lowercase r is just the rate of change in the amount of salt. So that makes sense because if you take the concentration, right, if you know there's 3 grams of salt per gallon, and you multiply that by the number of gallons per minute per unit time of solution coming in, that should give you the rate of change in the amount of salt coming in per unit time. Okay. Make sure, I might not be using exactly the same notation as the book. Make sure you read through the textbook. Okay. So I checked the textbook. I should be using probably capital R for the rate of inflow of salt, and I should use lowercase r for the rate of inflow of the solution, the mixture, like how many gallons are coming in. It doesn't really matter too much. Okay, so an example. I'll do part A first. Suppose the input rate of brine into a mixture is 6 gallons per minute, and the concentration of the salt in the brine is 2 pounds per gallon. Now, there's going to be an initial condition to this. Assume that the tank initially contains 200 gallons of brine, so that's a salt and water mixture, and the input rate of brine is equal to the output rate. Okay, so there's 6 gallons per minute are being allowed to come into this tank of 200 gallons, but at the same time, 6 gallons per minute are also leaving the tank. And it doesn't necessarily tell us how much salt is initially in the tank itself. Okay, not necessarily sure that's needed. Okay, sometimes, right, you might start with no salt in your mixture, right? You might have 200 gallons of water, and then you're pumping a salt solution into that water, and then also pumping some amount of water some amount of solution out of the tank. Right? So the idea here is you've got this tank. Let me draw a picture of this, by the way. I should have done this before. Okay, you've got some tank, and you've got some amount of inflow, right? You've got some water coming in. And then at the bottom, you might have another tube that is pumping water out. Okay. Now, let me make a little bit of room for myself. Let me actually redraw this just because I'm a terrible artist with the stylus pen. Okay. So you've got a tank coming in. Now, what it says is it's coming in at, let's see, 6 gallons per minute. Okay, and the concentration is 2 pounds per gallon. So 6 gallons per minute coming in, and it says there's also 6 gallons per minute leaving. Okay, so I guess the volume of the tank is never changing. You're always going to have 200 gallons inside. Okay. Now, what this says is that the rate of change with respect to time is, and I think I should be using capital R's. So sorry, that's the rate of change of the inflow of salt minus the rate of change of the outflow of salt. Okay, now I gotta find expressions for R in and R out. Okay. Now. Alright, so R in, that's how much salt is coming into the tank. Well, there's 6 gallons of water coming in per minute. You're going to multiply that by the 2 pounds per gallon coming in. Okay, so 2 pounds of salt. So this solution that's coming in, every gallon contains 2 pounds of salt. So again, you're going to multiply the concentration of the salt by the how much of the solution or mixture is coming in per minute. so 6 gallons per minute are coming in, times 2 pounds per gallon, well, naturally that's going to mean that you have 12 pounds per minute coming into the tank. Okay. So that's usually the easy one. Okay, now the outflow is not as easy to determine. Now here, again, you want to end up with units of pounds per minute. Now I'm still going to write this. Maybe I'm going to write this first. So, okay, there's 6 gallons leaving per minute. Okay, so that's how much solution is leaving this tank. And notice you're going to need the end result to be pounds per minute, right? How much salt is leaving per minute? Okay, you're going to multiply this by who knows what for now, but it is pounds per gallon. Okay, so how much salt is, what's the concentration of salt coming out of the tank? Well, what is the concentration would be this. So at any time t, there are actually a pounds of salt in that tank. Okay, and if you want pounds per gallon, at any moment t, there are actually 200 gallons of solution in that tank. And that's because there's 6 gallons per minute coming in and 6 gallons per minute leaving. So if you started with 200 gallons of brine, that would be your concentration at any arbitrary moment in time t. Right? So there are A of t, or A pounds of salt at any time, divided by the 200 gallons of solution in the tank. Now, there are times where the inflow might actually be slower than the outflow. Okay, so the amount of the number of gallons in the tank at any moment might be decreasing if you have more coming in than leaving the tank. If you had less coming in than what is leaving the tank, okay, then the gallons in the tank at any minute would actually be growing. But now I'm going to write down the differential equation. So, and I should probably actually finish writing this down. R out ends up being, okay, it's 6A over 200. It ends up being 3/100 A pounds per gallon. Okay, so that means the differential equation is the difference between those rates of inflow and rates of outflow. So the differential equation would be 12 minus 3/100 times A. Okay. So there would be your differential equation in that case. Okay. 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 So what if we repeat problem A? So part B, what if the output rate of brine leaving the mixture is 4 gallons per minute, but the input rate remains the same? Okay. So let's draw another picture again. You've got this tank. Right, you've got a tube for exiting water, or solution, sorry. You've got a tube coming in. It says, what's the only difference now? You still have 6 gallons per minute coming in, but this time it's leaving at 4 gallons per minute. Okay. Now, what do you know? You know that you start with, when you start filling and emptying this tank, you're starting with 200 gallons of brine solution. You don't know the initial amount of salt in there for this problem. Okay. So, let's see. dA dt. Okay, we know that's, again, the rate of inflow of salt minus the rate of outflow of salt. Now, Rn is not really going to change here. There's still 6 gallons per minute coming in, and that solution still contains 2 pounds per gallon. Okay, so that tells me that this is still 12 pounds per minute. Okay, so we have 12 pounds of salt coming into this tank every minute. Okay, now simultaneously, right, there's also going to be some rate of change in the amount of salt coming out per minute. Now there's, this time, 4 gallons per minute leaving. Okay. And then I have to multiply that by the concentration of salt in each per gallon. Okay, well, now this time, at any moment in time, you still have a pounds of salt. You need to figure out the number of pounds per gallon. Now, what you need to notice here is that now you need to find out the number of gallons in the tank at an arbitrary time. You're starting with 200 gallons. Notice you're going to be gaining more gallons of solution every minute. Well, if you have 6 gallons coming in per minute and you have 4 gallons leaving every minute, how many gallons are you going to be picking up every minute? Well, you're actually picking up 2 gallons per minute, and the number of minutes is represented by t. So, at an arbitrary time t, you have A of t pounds of salt in the solution, but the number of gallons that you're working with is, you have 200 plus 2t gallons, right? After 1 minute, there's 202 gallons. After 2 minutes, there's 204. So, in this case, the differential equation dA dt this time would be 12 minus that becomes 4a over 200 plus 2t. Okay, and that's a much more difficult differential equation to solve than the previous one. Now, another thing I want to point out is you could rewrite this differential equation as a linear differential equation. I'll write it this way. You could write this as a prime plus 4 over 200 plus 2ta equals 12. Okay. How do I know that this is a linear differential equation? It's because the right-hand side is a function of t, and the left-hand side is a linear combination of a and its derivatives, and the coefficients are functions of t. Okay. I'll write 1 out front. Okay, every term is a multiple of the derivative, and okay, 1 is a function of t, that's a function of t. So the left-hand side is a linear combination of a and a prime. Okay, the coefficient functions are functions of t alone, and the right-hand side, 12, is some function of time t. So this is a linear first-order differential equation. Okay, and the same would be true for part A. There might be other things you do on the homework. There might be initial value problems that you can do. If you have any questions, let me know. I'll halt the video there for now. Make sure to read the textbook, get the homework done, and I'll talk to everybody tomorrow at the Zoom meeting. Thank you.